This cartoon illustrates for us a physical system at equilibrium. We actually have water in a closed system, at least that's what these little molecules represent, and it forms gases in this upper region, and it's staying as a liquid down in this lower region. And this little water molecule is saying, I'm sure glad they evaporated. And that's just because that's where they are at equilibrium. Some of them are in the gas phase, some of them are in the water or liquid phase. And so those couple that are in the gas phase end up coming back in, and to be back at equilibrium, the other couple have to come back out. So it says, then I'm getting out of here. Today's standards are 7.1, understandings 2 through 3, application 2 through 3, guidance 2, and utilization 1. So what types of things does the rate of a reaction depend upon? We talked about this in the last unit, and the last unit and this unit go hand in hand, especially when we start talking about industrial processes. And so we just want to refresh a little bit on what those different things are with rate from topic 6. So we have things like if it's a gas, we can change the pressure. If it's a solid, we can change the surface area. We can change the concentration, and that's the big one that we're going to be dealing with in this unit. We can also change things like temperature and either the addition or non-addition of a catalyst to lower the activation energy. But again, concentration is the big one that deals with equilibrium. And so what is this topic, equilibrium? So an equilibrium constant, we talked about what is equilibrium last time. This time we're going to talk about a mathematical construct that we have, and we're going to deal with the constant that we can calculate for an equilibrium of any given system. So what is it first? It's the symbol K lowercase subscripted c, Kc, and the C, we're going to see what that stands for in a minute. The science definition, it's the concentration of the products raised to the power of their stoichiometric coefficients. If we remember back a couple of units, stoichiometric coefficients just mean those mole ratios from our balanced equation. So the numbers that are out front, the coefficients of those, that's my stoichiometric coefficients. So I'm going to need balanced equations for each of these. And that is divided by the concentrations of the reactants raised to the power of their coefficients, again, molar ratios. In summary, what this allows us to do, or it allows a reaction to reach equilibrium and then measure the concentrations of everything, combine the concentrations mathematically to get our constant for that specific equilibrium reaction. The equilibrium constant always has the same value, provided that you don't change the temperature. And that's irrespective of the amounts of A, B, C, and D. And what we mean by that is A plus B is in equilibrium with C plus D. Now that's just a general way of us thinking about reactants versus products. Sometimes, however, we have just one reactant decomposing into multiple products, or we have multiple reactants combining in a combination reaction into one product. This is just in general. A plus B yields or is in equilibrium with C plus D. It is also unaffected by a change in pressure or whether or not you are using a catalyst. If the concentrations remain constant at that equilibrium point, we don't need to look at it. For instance, solids remain constant in their concentration. They're not dissolved in the liquid, so if I have a precipitate, we're not going to have to worry about how much is there. So anytime I see a solid, I'm going to be able to ignore it. Or if I have liquid water and I have a bunch of aqueous solution, so it actually calls out water as one of the reactants or the products, I get to ignore it then, because that overall molarity or concentration is not going to be affected or changed at any points in the reaction. So I get to ignore it. So if you see a bunch of aqueuses on either side, then L for water, liquid water, I get to ignore that liquid water in my equilibrium constant. Now this number 5, this is a big deal when we're looking at creating our equilibrium constant, so put a big star by it. These are some little caveats to how we write our equilibrium equation that we don't want to forget. They're little tips and tricks, and we want to make sure that we don't accidentally put the liquid water in our equilibrium constant. So what's the point of this all? It provides a measure of the equilibrium's position. So whether I'm completely equal with both the reactants and the products, or if I'm forming more of my products at equilibrium or forming more of my reactants at equilibrium, And I can tell that when I calculate my Kc value. If my K is greater than 1, so we're going to see here what the reaction looks like. If it's greater than 1, that means the products are favored, and that's because that's on my numerator of my division that I'm going to be doing on the next slide. So if my numerator, the ones that are my products, are greater than my denominator, then K is going to be larger than 1. Think of it as 2 divided by 1. If I have 2 divided by 1, my answer is 2. That's larger than 1. That's because my numerator, the one that's on top, is greater than my denominator, my 1 that was on the bottom. Now, if K is small, the reactants are favored. That's because the reactants are going to be on my denominator, on the bottom of my fraction. So using those same numbers that I did in the last one, just as an example, it'd be like 1 divided by 2, which is 1/2, 0.5. That's greater or less than 1. That's because my denominator, where my reactants are, is a larger concentration than my products. If it's equal to 1, then my reactants and my product concentrations are equal. So let's take a look at the actual equation. Ooh, I hit it one too many times. Okay. My Kc value is equal to my concentration. Remember, we have brackets showing us concentration. If you think back to it, we've also used brackets for Lewis structures. So we see these things coming up in different points throughout chemistry, and we need to identify or look at other clues to figure out what type of thing we're talking about here. Here we're talking about concentration, which we've also called molarity. We've said that the units are moles divided by decimeters cubed, or moles times decimeters to the -3, or moles divided by liters, or moles times liters to the -3. We've used so many different ways of looking at the units for this and the ways of representing it. So we just want to remember all of those things and know that those are all equivalent. So here the square brackets are representing the concentration. That would be whatever my one product is, my other product, and these are those stoichiometric coefficients. So it'd be a 1 or 2 or 4, whatever it was to get it balanced. That's the number that goes up as the power that I'm raising it to. The right-hand side, so the side that I generally consider as my products, go on the top. The left-hand side goes on the bottom. And then it says here that the indices of the numbers in the front of each substance, that's the molar ratio of that chemical equation, is what goes as that superscript or that power. Notice here, we finally see what that C means. That C represents that this is my K value, my equilibrium constant, in terms of concentration. And that's all that we're going to deal with for our equilibrium constants in the IB standards. So here's our first problem. We have water as a gas reacting with solid carbon, probably like graphene or graphite, and that's in equilibrium. And notice that my arrow is wrong. This is the best way that I've been able to find to do it. It should be the forward arrow and then a separate backward arrow. In equilibrium with H2 gas and carbon monoxide gas. And all of the substances, do they have to be accounted for? No, they do not need to be, because of this one right here. The substance that does not need accounting for is B, because carbon is a solid, so the concentration is not changing at equilibrium, and so I can ignore it completely. The substance that goes on the denominator, then, my only other reactant, is H2O. So that's going to go on the denominator. My H2 and my CO are going to go on the numerator. So my Kc value, let's see if I didn't have it there. My Kc value is going to be H2 in brackets multiplied by carbon monoxide in brackets divided by my H2O in brackets. Now, it was already balanced, so there's no numbers that we have to raise it to the power of. And let's just go back here for a second, because we didn't talk about it too much. This multiplication is what's going on between these. So A raised to the power of the coefficient of A gets multiplied by the concentration of B raised to the power of, or the coefficient of B. So that's multiplication that goes on between them. So if you're using a non-graphing calculator, which you should be, we would probably take the concentration to the power first of each of them, and then do our multiplication, and then finally those products would get divided by one another to get the division that we see there. Okay, going back to this, we're going to look at this equation. First of all, first thing I notice is it's not balanced, so that's the first thing I'm always going to do. And I get a 2 as a coefficient in front of the ammonia, a 3 in front of the coefficient of the hydrogen, and a 1 as a coefficient in front of the nitrogen. It's products over reactants, so my NH3 is going to be raised to the second power. This is the only one that has that. Let's see if the rest of it is good. It gets divided by the reactants, my reactant here, N2, and H2 to the third power. Bingo, that is my correct answer right there. The other ones that I want to point out is B and C. We never just multiply by some whole number. It's always going to be the concentrations raised to the power, not multiplied by that value. Okay, here's a practice problem for us. We've got a synthesis reaction of hydrogen and iodine gases producing hydrogen iodide gas. At a certain temperature, the equilibrium concentrations of the H2 and the I2 are both 0.15 molar, and that of the HI is 0.50 molar. We're going to determine the numerical value of the equilibrium constant at that temperature. So first of all, I need a balanced equation. H2 plus I2 is going to form HI. To balance that out, I just put as 2 as a coefficient in front of the HI. And then I set up my general equation. My Kc value is going to be equal to the HI squared, because of that 2 there, divided by the H2 concentration times the I2 concentration. And now I can put those numbers in, and I get 11 is my answer once I type it all in. If you haven't done so, please pause this so that you can try it out yourself. Now, if I want the reverse reaction, that would mean that this would be on my denominator, and these would be on my numerator. So we're just flipping it around, and my value would be 0.090 moles over liters, or moles times decimeters to the negative 3, all of those equivalencies that we talked about before. Now, if you notice, the Kc of the forward reaction and the Kc of the reverse reaction are related inversely. So the Kc of my reactants is equal to 1 over the Kc of my products. I just flipped it around. So I could, rather than going through this whole process again, take 1 divided by 0.090, and I would, or divided by 11, 1 divided by 11, and I would get 0.090 moles over liters. So equilibrium is a highly studied process, and that's because it's utilized so much in industrial processes. Because industry wants to get the greatest output the fastest way possible with the least amount of cost and the least amount of energy input, while causing the least amount of waste possible. And they can start to do these things when they are taking a look at equilibrium, if we're forming equilibrium processes. So we need to consider, those industrial chemists need to consider both the kinetics as well as the equilibrium of the reaction, assuming that we can put it into an equilibrium process. The Haber process is one of these industrial processes that have been so vital and yet so scary for our world. It forms ammonia by this reaction. N2 plus 3H2 goes to 2NH3. And we're going to look more at this process later on. This is just in general what's going on. We heat it up, we've got a catalyst, we keep heating it up, and then we go down to where we cool it. Cooling it forms some of the liquid ammonia, and then some of it gets put back into the reaction, and we keep going around in a nice cyclical process as we form more and more liquid ammonia. We're going to talk about the Haber process both in a TOK manner later on in this week, and we're also going to talk about how or why they start this cooling process where they do, and why they have different pressures. So we're going to talk about